Hi folks, this is Heath. I'm recording in from an undisclosed location because I've got some technical issues at my house. But we're going to try again with section 14.3, so let's go ahead and get started. All right. So we're on a section on partial derivatives. We'll do a quick review of what we did in single variable calculus. When we were working with single variable functions, we talked about the derivative, and it measured how much, well, I'm going to have to get used to the positioning here. We're just in single variables anyway. Sorry, I'm learning the ropes here. Derivative measures how much the output value of a function, say we have this point right here, x naught, f of x naught, slope, there you go, and the slope is equal to the derivative of x naught. And so if the input changes by some amount, then the output will change by some amount also, but the output will change by some amount that's proportional to m. We sometimes call this the instantaneous rate of change, we sometimes call this the slope of the tangent line. And we use the symbol y prime or the symbol dy dx to denote this. And we sometimes use the mnemonic rise over run to remind us of what was going on here. Now that we're moving into 3 dimensions though, we have 2 inputs and 1 output. And so there is only 1 direction for rise, but we have 2 possible directions to run in. And so we have a partial derivative of the function with respect to x and a partial derivative with respect to y. Now I've written this notation that looks kind of clumsy, but if z is equal to f of x comma y, then this whole thing just becomes z, and we can write it like dz dx, using this little curly q d instead of regular d. And then this would just be dz dy. And so we can replace the function with just the output variable z if we want to. This one evaluates the rate of change of the function. If we allow x to vary, this is the one that allows measures the rate of change in the function. If we hold x constant and allow y to vary. So if I have some point, say x naught, y naught, and I have some surface, and this is kind of what the surface looks like. I'm just drawing a picture here. And x naught, y naught goes up to a point on that surface. So this is z equals f of x naught, y naught. Well, we have 2 different tangent lines to this surface. There's a tangent line in the x direction. There we go. And there's a tangent line in the y direction. In fact, we have more than 2 tangent lines, but we have a tangent line in both these directions. And the slope of this tangent line is the partial of z with respect to x. And the slope of this tangent line is the partial of z with respect to y. We'll do some examples in a moment, and I hope this will be a little clearer. I want to say one more thing about the notation. When you see this symbol, it's pronounced a partial derivative of z with respect to x. And sometimes when we're short on vertical space, we just write it with the f for the function with a little x. This is okay. Prime is no longer okay. Because prime doesn't tell us which input variable to use. It doesn't tell us whether we're using x or y. So if you like the prime notation and you want something similar, you can use a little subscript for the x. Don't put it up on top where the prime was, because that means f raised to the x power, and that's something different. But we can use this notation for a derivative. All right. So let's try an example. We're looking at the function x cubed plus x squared y cubed minus 2y squared. And we want to find the partial derivatives at the point 2, 1. All right. So we're looking at a surface. And again, this is not drawn to scale. But we have this point 2, 1. And that maps up to a point somewhere on the surface. And we want to find both of the partial derivatives at that point. So if we're trying to find the partial derivative in the x direction, that means we're looking for the tangent line to this point that goes parallel to the x-axis. And so the points that are on this tangent line all have different x coordinates, but they all have the same y coordinate of 1. So all of the points that are on this line have to form x comma 1 comma z. We don't know what x and z are because those are changing, but the y stays equal to 1 all the way through this line. And since y is equal to 1 all the way through this tangent line, I can replace y with 1 both times where it appears. And so this becomes x cubed plus x squared times 1 minus 2 times 1. This is x cubed plus x squared minus 2. And now that we're down from 2 variables to 1 variable, we can take the derivative. We can take the derivative here, and so the derivative of x cubed plus x squared minus 2 is 3x squared plus 2x. We don't have to work through this limit process to find that. Don't need this. But we could use it if we had to. But we can take the derivative without using the limit process. It's 3x squared plus 2x. And since we know what point we're at, this is 3 times 2 squared plus 2 times 2, because I'm plugging in 2 for x. And that's 12 plus 4, and that gives me a final answer 16. And so this slope is equal to 16. All right? So then let's keep going. Find the other slope. Before we do that, let's remind ourselves what we did here is I first, since we're working only in the x direction and the y doesn't matter, then we just replace y with a constant. That turned us from a 2-variable equation to a 1-variable equation. Then we could find the derivative using just ordinary single-variable calculus rules. Then once we found the derivative, then we substituted the x coordinate. In a little while, we'll be able to do this step up here. And in fact, most people do it that way. But either way is fine. Steps 1 and 2 are interchangeable. Okay? So let's try finding the derivative in the y direction now. So let's look at our picture again. 2 comma 1. Right there. And some surface in 3 dimensions. And the point 2 comma 1 maps to a point that's on that surface. Okay. In fact, it maps to point 2, 1, 10. How did I know that the z-coordinate was 10? Because I plugged in x and y and found what z was. And this time I want to find the slope in the y direction, so I'm interested in finding what tangent line runs parallel to the y-axis. Well, the points that are on this tangent line all share the same x-coordinate, because we're moving in the y direction. And so they will all be 2 comma y comma z, no matter what. And so no matter what happens on this tangent line, x is equal to 2. And so I can go ahead and plug in x equals 2 here and here. And I get 8 instead of x cubed, and 4y cubed instead of x squared y cubed, and 2y squared over here. There's no x to plug in over here. All right, now we're down to one variable. And so we can take the derivative. It's 12y squared minus 4y. And so that's the derivative here, 12y squared minus 4y. And again, we don't need this. In fact, it's wrong because I'm already took the derivative. I'm using the 12 and the 4. That was a typo. I should have gone back to the original function while I'm setting up a limit. Don't need this, and it's wrong. But when we take the derivative here and we plug in y equals 1, we get 12 times 1 squared minus 4 times 1, and that equals 8. And that's the slope of the tangent line in this case. All right? So what we did was we evaluated one of the variables, the one that wasn't changing, the one that remained constant, went down from 2 variables to 1 variable that way, then took the ordinary single variable derivative, and then evaluated the other variable. There is something called a partial derivative that's what we're going to look at here, and we can do that first, okay, before we have substituted either of the variables. And in fact, this is the method that most people use. And so from here on out, I'm going to try to show you how to do this using the partial derivative method. So same problem we did before. This is just an alternate solution. Okay? We're going to start with finding dz dx. So I'm going to look through this function, and I'm going to remember that after I have plugged in for y, I just have a single variable function for x. So treat this as if y was not a variable. Treat this as if y was a constant. And tell me how you take the derivative. So for this term, x cubed, the derivative of x cubed is 3x squared. That is a single variable function, so it's got the ordinary single variable derivative. Here we have x squared y cubed. The variable that we're looking to take the derivative with respect to is x. The derivative of x squared is 2x. And nothing happens to the y cubed part. Y cubed is just a constant in this problem. And so it behaves like a coefficient. It comes along, it doesn't change, it doesn't get larger, it doesn't get smaller. It just behaves the same way that an actual constant would have. If this had been 7x squared, the derivative would have been 14x. the x squared becomes a 2x, and the 7 doesn't change, it just combines with the 2. If this had been 9x squared, the derivative would have been 18x, and if this is y cubed x squared, the derivative would have been, the 2 comes down, we get 2y cubed, and times x, which is what we have here, except I've written this 2x times y cubed. But the idea is that nothing happens to the y cubed in the process. All right, and so let's look at this last term. There is no x in here. And so this is like 1 times 2y squared. But the derivative of 1 times 2y squared would be 0 times 2y squared. That is, the x part gets its ordinary derivative taken down, and the y part doesn't change. But the x part is just a constant, and so we end up getting 0 times whatever happened to y. We don't care what happens to y. But this is a constant in terms of x. There is no x in this term, and so any constant takes 0 as its derivative. And so the last term just becomes a 0. We don't actually write plus a 0, but it would be there. And that's where the 16 comes from. Plugging in 2 for x and 1 for y. That's the same answer we got before, but we're taking the derivative in a different way now. So let's try taking the partial derivative in the y direction. This is now dz dy. There is no y here, and so the whole term goes away. We treat the entire term as if it was a constant, because the one variable that's changing, y is changing and x is not changing, the one that's changing isn't present, so this really functions as a constant. It goes away. Then for this next term, where I have an x and a y, the y gets the derivative treatment. Y cubed becomes 3y squared, and nothing happens to the x squared. It stays x squared. It doesn't get bigger, it doesn't get smaller, the exponent doesn't change. Nothing happens to it. And then this last term is just entirely got a function of y. This is just a regular derivative. The derivative of 2y squared becomes 4y. And again, we're going to plug in 2 for x and 1 for y. And that's where the 8 comes from. 12 minus 4. So we get the same answer both ways, but we don't have to do the set of plugging in the 1 and then taking the derivative and then plugging in the 2. We can just take the derivative and then plug in the 1 and the 2 at the end. Okay? So let's try another example. Here's my function is x squared plus 3xy plus y minus 1. If you think you're doing okay on this, pause the video, try this problem on your own. And then unpause it and we'll walk through it together. If you had some trouble with the first example, just let the video roll. I'm about to do it, okay? So let's look at this example. If we want to find the derivative with respect to x, this has an x in it, and its derivative is 2x. This is a combination of a function of x and a function of y. The 3x part becomes 3, and nothing happens to the y. There is no x in either of these terms. And so the same way that the negative 1 disappears when we take the derivative, the y disappears also. Both of them go to 0. And then we were looking at evaluate this at the point 4, negative 5. So this is 2 times 4 plus 3 times negative 5 is negative 7. Now let's look at the partial derivative of the function with respect to y. All right. So I'm going to clean this out. So I've got to clean slide here. There's no y in this term, and so it has no derivative with respect to y, or it has a derivative and it's 0. then they have two terms here, 3x times y. The 3x doesn't change, and the derivative of y is 1, so it's 3x times 1. And then here, the derivative of y is also 1. And then the minus 1 is a constant, and so it goes away. Anything without a y, constants and functions of x, both go away when you take the derivative with respect to y. And then this is equal to 3 times 4 plus 1, which is equal to 13. All right, let's keep going. This time we're just looking at the derivative with respect to y. And we have y times the sine of xy. Well, we have two parts here, and both parts have a y in it. So we have to use the product rule. Well, the product rule says we take the first function times the derivative of the second function. So this is going to be derivative of sine of xy with respect to y, plus the second function times the derivative of the first function. And this is just a derivative of y with respect to y. All right. The derivative of sine of something becomes cosine of that same thing. And then we have to take the derivative of what's inside the trig function. Well, the derivative of xy, x stays the same because we're taking the derivative with respect to y. It doesn't change, but the derivative of y becomes 1. So xy becomes x times 1, which is just x. This one's easier though. The derivative of y with respect to y is just 1. So we end up with xy cosine of xy. I'm just combining my x, bringing that over to the front, plus sine xy. Okay? All right. So, quick review of some of the derivative rules. I don't think any of you need a refresher on derivative rules, but just in case, let's go through these kind of quickly. The power rule, if we have x raised to some power, the derivative became, that power comes down to the front, and then we subtract 1 from the exponent. So we multiply the expression by the exponent, and then we subtract 1 from the exponent. So now in 3 dimensions, where we have more than one input variable, we apply the power rule just to one variable at a time. Okay? So, a bunch of examples real quick. If this is my function, 3x to the 4th, y to the 5th, and I want to find the derivative with respect to x, then the x to the 4th gets all the love, all the derivative action, all that rich calculus-y goodness happens to the x to the 4th. The 4 comes down and combines with the 3 to make 12, and then the new exponent is x cubed, and nothing at all happens to the y to the 5th. But that's how it works. We're taking the derivative in the x direction, and so the variable x gets the action, and nothing happens to the y variable. Y remains constant throughout the entire process. Same function, but this time we want to find the derivative in the y direction. So the y to the 5th gets all the action this time. The 5 comes down and combines with the 3 to make a 15, and then the new exponent becomes y to the 4th, and nothing happens to the x to the 4th because x remains constant in that direction. Okay. If I want to find the derivative with respect to x, for 3x to the 4th, y to the 5th, plus 11y, well, in this term, the x to the 4th gets all the attention, The 4 comes down, becomes 12x cubed y to the 5th, just like in the example 3. But there is no x in this term. And so its derivative is 0. Anything that is a constant, the derivative is 0. And when we're finding the derivative in the x direction, y is a constant. And so if the variable that we are trying to take the partial derivative of does not appear in the term, the partial derivative for that term is 0. All right. The exponential rule. This is the rule that says that the derivative of 4 to the x is 4 to the x times the natural log of 4. And so the derivative of e to the x is, well, it would be e to the x times the natural log of e, but the natural log of e happens to equal 1. And so you're multiplying by 1, and that doesn't change the answer. The rule was we copy the term the way it was, then we put the natural log of the base over here. Now, if there's something in the x term besides x, we have the derivative of 7 to the 3x squared, then that became 7 to the 3x squared, and then we had to take the derivative of 3x squared, 6x dx. So if the derivative exponent has a derivative itself, we have to include that as well. So let's try some three-dimensional examples. Let's find the partial derivatives for this function here, 3x plus e to the negative 5y. In the x direction, the 3x becomes a 3, and the e to the negative 5y goes away because there is no x in the term e to the negative 5y, and so we treat the term as if it was a constant, and so its derivative is 0. There we go. But if we take the derivative in the y direction, this term goes away, and this term we're going to have to apply the exponential rule. We're going to get e to negative 5y, and then the derivative of negative 5y is negative 5. I'll put it over here where we others can see it, and then we take the natural log of e, and the natural log of e is 1. And so we get negative 5 e to negative 5y. Okay? Let's find the partial derivatives for this function here. Y cubed times e to the x squared. Okay? So that we have two different parts that are multiplied together. In the x direction, nothing happens to the y cubed, and the derivative of e to the x squared is e to the x squared times the derivative of x squared, which is 2x. In the y direction, now we're taking the derivative of y cubed, well that's just 3y squared, times nothing happens on the x side. The x side stays constant, e to the x squared. Okay. Trig functions, we do not have to learn any new rules. This is because on the very first day of the semester, I mentioned the importance of counterclockwise orientation, that going from x to y was counterclockwise in 2 dimensions. And so we arranged these 3-dimensional axes like this instead of going from x all the way to y, all the way to z. It's counterclockwise all the way through. One consequence of organizing the axes so that we never have to go counterclockwise to go up a letter, so that we never have to go clockwise to go up a letter, is that the trig functions behave the same way, and so they all have exactly the same derivatives. Sine of x goes to cosine Cosine goes to negative sine, tangent goes to secant squared. You do not have to learn any new derivative functions for trig functions. So let's try an example in here. We want to find the partial derivatives of x and y. Well, we have a term that is a product of two different pieces. In the x direction, 3x squared becomes 6x, and nothing happens to sine y. But in the y direction, x is still 3x squared, but sine y then becomes cosine y. Each half we take the derivative of separately. Okay? Alright, let's try this one. Cosine x times sine y. In the x direction, we'll take this derivative, and cosine x becomes negative sine x. And nothing happens to sine y, so it stays negative sine y. Over here, when we take the derivative with respect to y, this term stays the same. And this term gets the derivative, and so we have cosine of x, and the derivative of sine y is cosine y. Alright? We're making progress, but we've still got a couple of topics to go, so stretch or stand up or move around or do whatever you need to do to, get to the point. We're about the halfway point of this video. One more trig example. Find the partial derivatives for this function here. Alright, so the derivative in the x direction, any function that has both variables will split up, and 3 times y squared is going to be the answer for this. 3x becomes 3, and y squared doesn't change. We're going to have to take care of the e. It's e to the xy times the derivative of xy with respect to x, and that's just y. Sine of x becomes cosine x, and 3y over x minus 1, it might help to think of this as 3y times x minus 1 to negative 1 power. The negative 1 comes down in front, so it'll be minus 3y x minus 1, and it might be over the negative 1 now becomes a negative 2. Let's see if that works. Okay. Alright, we have to still find fy. So this time we get 3x times 2y, which is now just 6xy plus e to the xy times x. Sine x, we don't have to worry about the trig function at all. There's no y in it. And so its term is 0. And then 3y over x plus 1. Since we're taking the derivative in the y direction, the derivative of 3y is 3, and nothing happens to the x minus 1. All right. Let's look at the implicit differentiation. Back in section 3.5, back in single variable calculus, we did implicit differentiation, and there was a whole process to it. We had to take the derivative on both sides. Every time we encountered a y, we had to put a y prime or a dy dx at the end of that term. Then we had to separate out all the dy dx's and factor and solve. Oh, it was a lot. But partial derivatives give us a faster way of doing differentiation. And the trick is that the derivative dy dx is orthogonal to the partial derivatives f sub y, f sub x. So this is the ordinary implicit derivative. partial derivatives. But we're talking about a slope here. And a perpendicular slope is a negative reciprocal. And so we can replace this with dy dx is the negative reciprocal of the partial derivatives. So fx goes on top and fy goes on bottom because we're taking the reciprocal. Okay, let's see how easy this is to do. It'll amaze you if you remember during implicit differentiation. The first thing we're going to do is group everything together so we just have one function. And the other side is equal to 0. It doesn't matter which side is equal to 0. If you put everything on the right side, there will be a sign change up here, and there will be a sign change down here, and the sign changes cancel each other out. So it doesn't matter. Put everything on one side, make the other side 0. Think of that left side as a function and find the two partial derivatives. So we have x squared plus y squared minus the sign of xy. The derivative of x squared becomes 2x. Y squared goes away with respect to x. Sine becomes cosine. And then the derivative of xy is 1 times y, which is just y. X becomes 1 and y stays the same. Then in the y direction, the derivative of y squared becomes 2y. Sine becomes cosine, and the derivative of x times y becomes x times 1. And then we're going to arrange these into a function, a fraction, but in the opposite order. We're taking the reciprocal, remember. And so if we want to find dy dx using partial derivatives, I want the partial derivative with respect to x on top and the partial derivative with respect to y on the bottom. So that's this here, partial with respect to x, partial with respect to y. And then the last thing is we don't just want the reciprocal, we want the negative reciprocal. So we're going to take the negative of what we just did in step 3. If you don't want to think of it as 4 different steps, we can just say, just remember, take the negative reciprocal. Okay? So the partial derivative of y with respect, or the derivative with respect to y. Let's try that again. The derivative of y with respect to x is the partial derivative with respect to x over the partial derivative with respect to y, but made negative. All right. Let's do some means. If x squared plus xy plus y squared minus 7 is 0, find dy dx at the point 1, 2. So dy dx is the negative of fx over fy. So that's the negative of, let's take the partial with respect to x. With respect to x, x squared becomes 2x. xy becomes 1 times y. X goes to 1, y doesn't do anything. Y squared has no x in it, and so it goes to 0. And 7 has no x in it, so it also goes to 0. So we just get 2x plus y. Alright. Now we'll do the same derivative with respect to y. There is no y here, so this goes to 0. The derivative of y is 1. And so this goes to x times 1. The derivative of y squared is 2y. And the derivative of negative 7 is negative 7. Or no, the derivative of negative 7 is 0. And now we'll do at the point 1, 2. So we get the negative of 2 times 1 plus 2 over 1 plus 2 times 2, which is the negative of 4/5. much easier is that than what you have to do back in 1225. Once we can do partial derivatives, we can do implicit differentiation much easier. All right, so we've talked about derivatives. If we have to go to second derivatives, if we want to talk about concavity of a surface, we can do that, and we will do that. But we have to talk about the idea of higher order partials. If I have a function of two variables, there are two first derivatives, because I can take the derivative of the function with respect to x, which we abbreviate f with a little x, or we can take the derivative of the function with respect to y, which is f with a little y. But when I take the second derivative, that's the derivative of the derivative, and so I have to make that same choice again. And so we end up with 4 second partial derivatives. Start with fx and calculate the second derivative, again with respect to x, or starting with fx, even though we use x for the first derivative, we're going to use y for the second derivative. That gives us some information. We'll talk about what fxy means at some point, but right now we're just learning how to do it. And then fy, we can start with fy and then take the second derivative with respect to x, or we can, I mess this up, take the second derivative with respect to y and the first derivative with respect to y. So there are 4 different partial derivatives here. Okay? So let's find all 4 second partial derivatives from this section here. Excuse me. Okay? So let's first find just the regular first derivatives, fx and fy. Fx, this is x times cosine y, so we get 1 times cosine y. This is y times e to the x, so that stays y times e to the x. E to the x becomes e to the x, and y doesn't change. But with respect to y, we get x times negative sine y. And y times e to the x becomes 1 times e to the x. So now we're ready to find the second derivatives. fxx, there is no x in this term, so it goes away. And this is still y times e to the x. The derivative of e to the x is still e to the x, and nothing happens to the y. With respect to y, cosine y becomes negative sine y, and y e to the x becomes 1 e to the x. All right. Then here we have fyx, and then later we'll have fyy. Fyx, I'm starting with fy and then taking the derivative with respect to x. So the derivative of minus x is just minus 1 times sine of y. So minus sine y. And the derivative of e to the x is still e to the x. And then fyy, the derivative of negative x sine y would be negative x cos y. And e to the x doesn't have a y in it, so it goes away. And one of the things I want to point out is that this partial derivative and this partial derivative turn out to be the same. Both of these turned out to be negative sine y plus e to the x. That is, taking the derivative of x and then y gave me the same answer as the derivative of y and then x. Does that always happen or just sometimes? Well, the answer is in Clairaut's theorem. And what that says is that if the partial derivatives are continuous, say we're looking at some point x naught, y naught, and the function may have some discontinuities, but if there is any kind of disk, no matter how small, that separates this point x naught, y naught from those discontinuities. So there are discontinuities somewhere in the graph, but this point is not immediately adjacent to a discontinuity. I can separate it from a discontinuity by drawing a little disk around. Then, at least along that disk, the two partial derivatives will be equal to each other. So, at any point that can be separated from this discontinuities by a tiny disk has this property. Well, in practical terms, almost every function that an engineer would ever work with behaves this way. All of the functions we covered in single variable calculus, sines, cosines, trig functions, inverse trig functions, exponential functions, logarithms, roots. In practical terms, it means that really the order doesn't matter. That we can just treat fxy and fyx to be the same. There are some exceptions. There are some functions that have an infinite number of discontinuities that are so spread out on the plane that no matter what point you pick, if you try to draw a disk, you'll end up hitting one of those infinitely many discontinuities. That can happen. And it requires having not just an infinite number of discontinuities, but having them so spread out that you can never isolate points from. That is a really challenging function to come up with. You can do it, but it's hard to come up with a function that does that, okay? So, for practical purposes, the order of taking a derivative doesn't matter. As a technicality, yes, it technically does, but you are very unlikely to ever see an example where you will have to worry about the order mattering. Personally, I can tell you, I never saw an example until I was in grad school. My second semester of graduate school, we constructed a function that was a counterexample to Clairaut's theorem. And it took a whole period to build that function. And that was after I'd had, an undergraduate degree and a semester of grad school under my belt. These things do exist. They were very hard to build. You were very unlikely to ever see one. Okay? So I would like to tell you this is a theorem that works in all cases. It doesn't work in all cases, but I don't think you have to worry about the exceptions. I'm going to move on. We can use this theorem to our advantage, though. If I want to take a long, complicated fourth derivative here, I can do it in the order that is most pleasing to me. For example, I only have one term that only has a z in it. This term doesn't have a z in it, this term doesn't have a z in it. So if I do fz first, then the 1 goes away, and this term goes away, and then this becomes negative 2xy squared times 1. And so instead of having 3 terms, now I just have 1 term. Then if I do fzx, I'll do x next. Because this is x to the first, the derivative of negative 2x is just negative 2, and nothing happens to the y squared. Alright, then f of zx y will be negative 4y, and f of zx y is negative 4. But even though I did this in a different order, zx y in the problem after yx yz will be the same. We have a theorem that says the order doesn't matter in almost every case, but there are no discontinuities at all here. We know this function is entirely continuous, so we are 100% certain that this function is not going to be one of those exceptions. Takes much more than that to build an exception. Okay. Here's an even better example. If I want to find w of yx, the instructions say to do y first, but that means having to use the quotient rule here. Ugh. You don't like quotient rule. Quotient rule make me sad. But if I do x first, well, the derivative with respect to x of xy, x becomes 1 and y stays the same, so we get 1y. And now there is no x here. And so the derivative of any function with respect to x that has no x in it is 0. So that whole function goes away and I don't have to use the quotient rule. This is actually just wx, not wxy yet. And now we'll take wxy. That's the derivative of wx with respect to 1, with respect to y, which is equal to 1. And so we get a very simple answer, but if we had done it in the way the problem had asked us to do it, we would have had to use the quotient. Okay? All right. So thank you for putting up with this alternate conditions video. I hope everything is going to be just fine back at home for Friday. I will see you then. Take care.